Well, Johnny already gave you the overview of the CEEDS project. And so I would like to give you a bit more of a sense of, let's say, the key scientific considerations behind the project and how we translate that into technology and into this specific CEEDS paradigm that Johnny already outlined to you. So I will start talking a little bit about big data and why this issue of big data is so relevant right now, and why this also has very unique challenges that we have to address, I believe. And then from there, I will draw some conclusions that will bring us to this idea, okay, there are some key steps missing in this sort of meaning chain, if you want, from big data that we try to fill in with the CEEDS project. Important to keep in mind, of course, Johnny already laid out to us, this is a large integrated project, so there are many partners involved. So what I'm talking about is certainly not only the work of SPEC, my research group, but it's really a collaborative effort across all the partners of this project, but I might not mention all of them all the time. But just keep this in mind with respect to the technology that I'll be discussing. So this is a scientific instrument that actually changed the course of our history as humans. Right, because this thing actually has an aperture, and this is the telescope that Galileo built based on an earlier design by Dutch spectacle makers. All right. And Galileo built this telescope because the idea was there, the idea of the Copernican revolution, right, that our planetary system might be all revolving around the sun. The idea was around, but the data was missing. And here, Galileo understood that if he would have an instrument to be able to observe the planets, he might actually get additional data that would help him to now make a key decision, right? Is it right or wrong? So that's what he did. Here we see him demonstrating this to the Doge in Venice in 1609, and he observed the faces of Venus, right? The shadows that you would see on Venus as it revolves around the sun. And this clearly indicated to him that Copernicus had been right. So, and this then changed our whole view of the universe, of God, and everything that followed. So what we see here in the case of Galileo is that the idea was there, but not the data. Data was expensive, right? Data had to be fought for, it was hard to get. And it also meant that the theory that Copernicus had advanced had to be supported by observation, but the observations are not always easy, right? So that also then gave Galileo, if you want, the honor of defining what's called, if you want, the standard model of scientific inquiry, where from our theory we will deduce our predictions, right? Or from our observations we will induce theories or rules, okay? And it's in this loop between theory and observation that we try to evolve and then advance our understanding of reality. Okay, so far so good. And indeed, if you now then start to pose the question, but how do we really know that the theory actually means anything? Right, and actually scientific theory, and then the scientific theory is, if you want, that collectively as humans you would say, this is the best and most advanced form of knowledge that we have of the universe. Then our theory, scientific theory, should have a number of properties. They should be able to explain, predict, and control. They should be able to explain phenomena. They should explain why the shadows of Venus are what they are. Right? They ought to predict. For instance, they could predict once this was the Copernican view of our solar system was merged with the Newtonian view on gravity and gravitational forces being proportional to the mass of objects. Suddenly, the wobble in the trajectory of Uranus was actually predictive of the existence of another planet. And indeed, that became Neptune. Right? That's how Neptune was discovered. A very classic scientific event, because for the first time, a mathematical consideration made a prediction that was validated. But thirdly, that's often a forgotten aspect of scientific theory. We want to control. We want to control reality. You think about building a new experimental apparatus to test a certain prediction. It's also part of controlling reality. Or you build a device that might fly because you have a theory about flight. Okay, so the three criteria of scientific theories are explain, predict, and control. And this is going to be important when we're going to discuss the data, the big data challenge of today. And indeed, if we now jump to the life sciences here at Watson and Crick, it's a few centuries after Galileo. And Watson and Crick had exactly the same problem. What we see here is that for Galileo, the language of the universe is mathematics. But here you see that for Watson and Crick, the language of nature is a different one. It's a physical model. Right? Their theory in the end was a physical model. But if you read their autobiographical notes on this period, you see they're anxiously waiting for the data, right? That Rosalind Franklin has to produce. She does X-ray diffraction on DNA molecules, and it's through these diffraction patterns, so the scattering of X-ray by these molecules, that you can actually make then inferences about the shape. And those shapes, they then try to reconstruct using these mechanical models. And the big discussion was, for instance, okay, is the backbone of DNA at the outside or at the inside? Okay, and the diffraction data helped them to resolve that ambiguity. But then again, here we saw there was an idea, right? Actually goes back also to Schrödinger. If you read his essay, What is Life? He's predicting the role of DNA in the inheritance of our genetic properties. And then Watson and Crick actually gave substance to that idea and validated it with data. And then something interesting happened. Okay? So Watson and Crick is now here in the 1950s, and here we look at all the publications in the life sciences since the 1950s till about now, and we see exponential growth. All right? So we see after the 50s this incredible increase, and now we're talking about 1 million publications a year or so in the life sciences. And what you have to keep in mind about every publication is a data set, effectively. Okay, most publications in the life sciences is somebody reporting on some data they collected. All right, so this gives you also an indication of how our data is exploding. And another way to look at that is this is about the size of a standard DNA database, 15 terabytes. But if you go to other disciplines like climate research, you see that we talk about orders of magnitude larger data sets. And now actually in 2020, the so-called square kilometer array will come online, which is a radio astronomy measurement system, which will generate 22 billion terabytes of data a year. The authors of this claim that's larger than the capacity of internet, but then when I tried to find out what's the capacity of internet, no one would tell me. So okay, it's a large number, all right. And but the point about this is you see what happens in Galileo, right? Now data is cheap, but ideas are becoming more and more expensive. All right, you really get the gist of the story here. So we have big data. Big data is easy, right? You can use your phone and generate loads of data, like, oh, there's me walking through London, I hold amazing data. And some people call it also data deluge, right? That this is, we have to keep a firm eye on this issue, that of course more data might of course also mean that we will drown in it in terms of our understanding of this data. All right, so more data doesn't automatically imply understanding. So now this problem has been addressed in the life sciences in some sense. Okay, so let's now look at the consequences of this. All right, so here I have split out the data in neuroscience on publications with keywords in the title or abstract of neuron and brain, stroke and rehabilitation, and theory and brain. Okay? And we see that they're sort of keeping up if we normalize them to their own totals. The growth keeps up, but a little difference in the offset, like theory became a bit more popular later than, let's say, understanding of stroke. So, but a lot of data here and a publication on the brain, a lot of certain deficits of the brain, and also we have theory, okay? But this increase of data doesn't also translate in an increase of understanding, doesn't improve our grasp of reality. Well, now recently Button and co-workers published a really nice review paper in Nature Review Neuroscience, where they basically show that most of the neuroscience studies are underpowered. That means the number of the the sample size they consider is often too small for the conclusions they want to draw. Now this might sound boring to you, but this is very important because it means this exponentially growing curve, where we look at 1 million publications a year, what this meta-analysis shows that the majority of these publications have a power in the range of 8 to 31%. That means their probability to actually report something that is real is fairly low. Okay? So this is now a problem because we have a lot of data, but also we have uncertainty about what it really is reporting to us. Is it an artifact or is it really out there? Secondly, and this is the winner's curse that they also put their finger on, with lower power, the probability to report artifacts goes up. Okay, so they might just be reporting spurious effects that are resulting from very small sample sizes. Again, this might sound like boring statisticians stuff, but that's not true. Okay, because the point is the trend in our world, and you're all part of this, is big data. You all read these studies like, oh, Facebook has measured of 10 million people and do all sorts of things and whatever, and then they see these minuscule fluctuations in the data. The statistical significance of data matters now because we talk about large numbers of observations. Okay? This doesn't mean all data is bad, but it means we have to be cautious. So, I told you earlier, the criteria of scientific theories is to explain, predict, and control. Now, if we look at this meta-analysis of neuroscientific data, it shows this data cannot just explain and predict, because the majority is apparently reporting things that are spurious, that don't exist, that are artifacts. So they're not explaining or predicting anything. Not good. All right, so big data is not helping us here. Now the second thing, this is an analysis I did with a colleague of mine, is okay, let's look at this issue of control. Is our ability to measure more of the brain also enhancing our control of repairing brains that are broken? Now if you take stroke, that's like the simplest deficit of the brain you can imagine, because it just means there's a hole in your brain. Neurons are gone. You know what the problem is. There's just a piece of tissue that has died, that's necrotic. It's not something like Parkinson's disease where you have very diffuse changes to the brain, more difficult to control, and schizophrenia. Okay? This is a well-defined problem. So now here what we analyze, these are about 24 meta-analyses of the impact of stroke rehabilitation using the same clinical scales. And what we see, which really astonished me, is that the correlation over time is 0. So from 1975 to about now, right, our ability to influence stroke recovery in the face of an exponentially growing database has stayed the same. All right? I think this is shocking. So that means we also have no control. All right? So what I show you now, we go back to our old friend Galileo. He tells us what the scientific theory is about. Okay? Explain, predict, and control. He had to fight to get his data. Now data is cheap. We get it for free. But we lost our ability to explain, predict, and control with no more theory. This is our problem. By buying into cheap data, we became empty-headed and have given up on theory. All right? And this is a problem. Because it's only when we give meaning to this data that we can actually have an influence on reality. All right? So this is not just a frivolous issue. It's a fundamental problem. So, that's our challenge in the CEEDS project. So how do we go now back from big data to some sense of understanding? All right, how do we now fix this problem? Well, some people have tried in let's say, pragmatic ways. So I was a member of the OECD Global Science Forum on neuroinformatics in the mid-90s to the early 2000s, where we discussed about unifying neuroscience data. All right, to at least try to find ways that data is, let's say, easily shared and reused and so on. All right, so that was one step, which has led to the creation of a special institute in Stockholm that does that. And, however, the impact has not been that amazing. And right now we see that both in Europe and the US, massive initiatives are underway to try to tackle the brain, right, to understand the brain. But again, you see the emphasis on generating more data. Like a human brain mapping project in the US, it's all about building new probes, building micro robots that can go in the brain, get more data, and so on. If we just saw more data, it's not automatically solving our problem. So we'll just go like this, but still the same associated problem. So how do we go from big data down to a solution of this problem? So for me, big data is the problem, and it's not our solution. So this is our solution. This is an experience induction machine in which we have built a technology that is trying to assist researchers in a very specific way to get a grip on big data. So our problem domain is the brain, right? The brain is this incredible organ produced by evolution that brings us from the past into the future, but it creates this future by actually learning about this past. Right? It's an amazing adaptive device that actually defines everything that we are and everything we experience. Everything we are is our brain. It's an extreme way. Of course, you might want to give your body, but okay. The brain is essentially it. The problem of the brain, and that's what makes it different from Galileo's problem, is that the brain is defined at many levels of organization. From the molecules that make up the ion channels that allow electrical currents to flow and neurons to generate spikes, to, let's say, societies, cities, or even the world, right? Our collective brains are able to change the climate on this planet. It's amazing. So, brains are organized at many different levels of organization. That makes it a unique problem. So how do we get now to some better understanding of this brain? Well, let's first look at this issue of control. Can we exert better control over brains that are broken? Well, actually, we built a mixed reality neurorehabilitation system where we, based on theory of how the brain operates, which I will not really explain now in great detail, we made a list of about 12 criteria to which rehabilitation protocols should obey in order to be effective in rehabilitating a brain that has a hole in it due to stroke. And we now have tested this on acute and chronic stroke patients. We have treated a few hundred patients by now. And we can show that this works better. So here we see, for an increase in speed over time with the patient group. These are the control groups. This works better than the standard treatments you can get today in the clinic, like occupational therapy. All right? But we went here from a theory to controlling the recovery of the patient. Okay, we didn't follow the standard what's called evidence-based approach, where any correlation is great. We went for a science-based approach, where it was the theory we were testing. And actually, on top of that, we were able to predict specific patterns in the brain that had to occur if these principles were at work, and we found them also using fMRI. Okay, so far so good. So it's possible, right, to really go from theory to our data. Following the more traditional model is feasible, but it's still not enough. Because how can we keep up with big data in terms of generating our new hypotheses, right? In the past, there were hypotheses in which we might be capturing data, but now we have the data, we have to sort of catch up with our hypothesis. This is the tool that we need to think about. So how do we build a hypothesis accelerator? It essentially means you have to think about a technology that taps in what's called the logic of discovery. It's an old debate in the philosophy of science, where you have the logic of verification, what makes knowledge true, right? And you have the logic of discovery. How does the human mind discover new things? And we want to move now more to this issue of the logic of discovery. And actually, Charles Sanders Peirce, the famous pragmatist, American philosopher, late 19th century, had a name for this. He called it abduction. But look, it's not only about deducing specifics from general knowledge or induce general regularities from specifics. In between here is the creative step, which I call abduction. That's where your world model changes, if you want, where you have an insight, where you generate a new hypothesis. So how can we build a technology that can help the researchers of today abduce right? To deal with these big data sets in an inductive sense. For that, so this was our first axiom. How do we get abduction? How do we build a technology that can feed abduction? So the second axiom then is, okay, we have to tie this to creativity. Right? There's some things are known about creativity, not a lot, but some. And most of the stuff we know that is solid goes back to the 19th century, to people like Helmholtz, who would actually see different stages in creativity. And what's interesting about this is that there are like subconscious components and conscious components. He would say, look, there's a preparation and exposure phase followed by incubation, where you're just not aware, you're not consciously dealing with the issue. But it runs along in the background somewhere. And then there will be this moment of insight, of illumination and verification, where it becomes conscious. So what we try to achieve now is to build technologies that can help this preparation incubation phase, right? To facilitate and to accelerate our ability to generate new ideas about the data that we're dealing with. So incubation is a subconscious process. John also alluded to this in our third axiom. Essentially, and there's a number of theories on this, like global workspace theory, dynamic core, Bars, de Haan, Jerry Adelman, other people. The bottom line is that it is this Cartesian fallacy to believe that our conscious mind is the determinant of our behavior. It's not. Right? There are classic experiments that show that our consciousness is always lagging behind real-time operation. Famous Lisbeth experiments, right, from the 70s. So, and even Wagner has pushed this further by saying, well, the causal relationship between action and our mental states is fully subconscious, and the conscious pathway is more like a post hoc rationalization. So that means if we want to drive creativity in a scientist, we have to find a way to access this subconscious pathway. This is what we want to achieve. So how do you do that? Right, so you can rely on miscellaneous magic, but we thought we could do better than that. And it looks a little bit like this. We have a data set, we have a user, but in between the data set and the user are a number of stages of processing. On the one hand, it's an range of presentation methods of this data, so the user can basically select different ways to view, interact with the data, but not only visualize it, also in real time analyze it. And there, at the other end, we are analyzing both conscious and subconscious or implicit and explicit states of this user. In particular, we extract implicit states by looking at the states of the autonomic nervous system. Think about arousal, change in heart rate, breathing, of any skin response. But you can also look at the EEG. Change in EEG might tell you something about the predictive capabilities of brains and so on. So, we extract implicit and explicit channels to, in some sense, make the subconscious conscious to this user. Okay? Why is that important? Well, the point is, our brain is also fooling us all the time. We are going through life in real time based on heuristics, and some of these heuristics bias our decision making. You might be familiar with confirmation bias. You walk in your doctor's office, you haven't opened your mouth yet, he already knows what's wrong with you. Right? From then on, we only pose questions to confirm this hypothesis. We tend to confirm what we expect. This is not the best way to gain knowledge, right? Or things that we have seen a lot look more trustworthy, look more reliable, even though they can be completely wrong. It's just a frequency of observation that counts. Okay? So this is very much what's driving our conscious states. But we have to bypass also these biases, and that's why we want to enter at this subconscious level. Again, we do this based on a theory, which I won't explain to you, just to tell you it's all true. This is a theory I've developed on mind and brain over the last 20 years. The key thing is, this is what drives our technology, because now we're again testing a theory directly. So the technology fails, the theory is wrong, and we learn something. That's good. So actually, and I will step through this rather quickly again, we have mapped the whole Ceeds core architecture that presents data, measures the user, makes decisions, chooses certain narrative pathways to present information. All it is mapped to this architecture, an architecture again of mind and brain. So we try to be as systematic as we can. And what does that look like? So here we have a person exploring the connectome. This is what we have now. So we have wearable devices like a vest that measures heart rate, breathing, electrodermal response. We have a glove that allows the user also to point and grab virtual objects in real time. We get now all these measurements of both implicit and explicit states of the user. And we have now also augmented this with eye tracking. So essentially we have our XAM space. We track in a labeled fashion groups of people in real time. And now these people can wear eye trackers so that we also can know exactly what people are looking at in real time, combined with pupil dilation, which is an interesting measure for cognitive states. So we have mapped this now to the virtual objects. We have the intersections. So here's an example. Here this is a little test of the system. So that now means that we have basically full access to all possible states of this user, including their eye movements. Eye movements have both unconscious and conscious components, right? So you want to have both of these available to you. So with that now, we think we can generate big data, big ideas from big data. So I'll give you an example now how this is done. So here, for instance, now the workspace is organized in case of the neuroscience application as this is the instantaneous workspace of the user. Time flows in this direction where we have basically unconscious states on one side of the space, conscious states on the other side. We call this discovery and hypothesis. And here this is more like a memory, a log of all connectivity that the user can resort to later to get like a map of how they have explored the data. So here's an example how this works. So with Alberto interacting with a human connectome, every dot is an identified location in the brain. He can now inject activity in these nodes and run simulations to understand how these nodes are also connected dynamically. It's actually quite a problem if you look at brain data. It might tell you something about structural relations, but not about functional relations. So here, Alberto sorts the data in real time in terms of complexity. So he can now see what are the key hubs in communication and what are more the peripheral nodes in this system. And again, he can make a virtual lesion, he can take out a number of them, and again see, okay, how does this interact? And how we're now using this is to also as a diagnostic tool again for our stroke patients. Because now I can try to understand better, okay, if I have a defined lesion of a certain patient, what are the knock-on effects of other parts of the system? These are capabilities that don't exist today in the clinic, but we think we can make them available in this way. So you see, Alberto is now interacting with this complex data set. It's about 1,000 nodes and 39,000 connections among these nodes in a fairly intuitive way. And the key thing is just, it has to give him all the tools to develop hypotheses on functional relations in this brain. With that, he can go back to a patient, he can go back to a laboratory experiment to test that hypothesis. But this should give him the control over that complex data set. Okay? Yeah, okay. 2 hours, yes, okay. So, the point is, and this is often a problem in this domain, big data is too important to leave it to the engineers, all right? So, because what often happens in this domain, people build something cool, like yesterday I had some guy presenting stuff to us about data visualization. And it's all cool, okay? But you ask him, but how do you know whether this works? I said, well, no, I don't know, but I like it. And that's just not good enough, right? Because a scientific theory should explain, predict, and control. So therefore what we do is also we go back and we perform more psychological experiments. Okay, but does it really have an impact? So this is one of these experiments on the data you just saw, where we have one group of subjects work with the state-of-the-art connectome viewers that are used everywhere in the world, and in green, okay, versus a group of users that is using our system. And afterwards, they're just asked to explain what's the causal structure in this data. What is the connectivity exactly? So it's a very objective measurement of understanding. Either you say A and B is connected or you say it's not, right? So it's very simple. And what we see here is that in our case, for different measures, also accepted measures of this structural understanding, using this system shows a higher level of deep understanding of causality in these models than using the state-of-the-art tools. So we believe that with that we're on the right track. This will work. So, from big data to big ideas, some conclusions. What we often forget is the primary and most important instrument of science is the human mind. And we cannot replace that with big databases and search engines. All right? Rule number one. So that there's no salvation in automatic solutions, machine learning, whatever. It's not going to happen. So the ability to generate data is outpacing our ability to understand it. So John Doyle, a good friend of mine, control engineer from Caltech, we should stop this pedophilia. Right? It's not about getting more data, it's about understanding it. So big data right now is the problem, not the solution. And with Seeds, we try to build new instruments to help the human mind to catch up with data of this kind of complexity and scale. So let's call this the XCM hypothesis accelerator, or the Seeds hypothesis accelerator. So we constructed this, we applied this successfully to this neuroscience data set, and I showed you by really measuring understanding in our users that it looks like we're onto something that could work. All right, so we in that sense are very optimistic. We have other applications. One, as Johnny mentioned, is with respect to the Holocaust and the Bergen-Belsen Memorial Site, where you have another problem to solve. I will show you a very short video clip. I think it's an important one. I want to show it to you. And the second domain is then archaeology. So this is a 1-minute clip to give you an idea of what we do with respect to the Holocaust.
Aber es ist so friedlich. Es ist so schön. Die Heide, die Bäume, die Vögel. Es ist ein Naturreservat. Das war es nicht. Das war genau das Umgekehrte.
I have just returned from the Belsen concentration camp, where for 2 hours I drove slowly about the place in a jeep with the chief doctor of Second Army. I find it hard to describe adequately the horrible things that I've seen and heard, but here, unadorned, are the facts.
All right, so again to tell you, it's not about data, it's about meaning. And meaning that we find in many different domains. And the Seeds project tries to build a new technology to help humans find data or find meaning in the data we extract from reality. Thank you.